when we need to find, and we'll look at an example, review an example of one where we need to find the second derivative. The second derivative has a few applications, and we'll look at one, but before we do that application, we better, first of all, talk about how we find the second derivative of parametric equations. If we have parametric equations. First of all, the notation they use for second derivative is a little different than we're used to. You know, second derivative, we're used to the double prime notation. Well, that's not what we use here. Of course, we know that the second derivative is, well, it's the first, it's the derivative of the first derivative, right? So it's the ddx of y prime, usually, if we're using our Cartesian notation there. Okay, and so that, of course, also could be written this. So the second derivative could also be dy prime over dx, right? That makes sense. You're just doing the derivative of the y prime. Well, to further, this is that's kind of mixed Leibniz notation and regular notation because you got the y prime. If we use strictly Leibniz, it'd be, that's y prime is dy over dx, right? So it's the ddx of dy over dx. And I do that one, we won't use that one much, but here's actually the one they use the most. If you look at that, it kind of helps you understand this this notation that they do use. It's d squared y over dx squared. You kind of see sort of where that comes along. Well, for whatever reason, they choose to use this right at this particular moment in this particular part of the book. So if you see that, that's just another terminology, another notation for the second derivative. So d squared y, even though just looking at that, that's not at all automatic, you would think second derivative of that, but that's what it means, okay? That's just another notation for the second derivative. Okay, so the question then is, how do we find that second derivative, or d squared y over dx squared, if we have parametric equations? Well, if we think again, so for parametric equations. Well, d squared y over dx squared, again, that's probably not the most useful of, I guess it's useful in some ways, but what this is, it's a second derivative. It's the derivative of the first derivative, right? That's what the second derivative is. Let's use this. Now, if we've got parametric equations, both of these then, the y prime is in terms of t, the x and y are in terms of t, and so what this amounts to is I need both of these. I need to take the derivative of y prime with respect to t, and then the derivative of the x with respect to t. It kind of looks like you're dividing both sides by t, but essentially you're just taking the derivative of both of these with respect to t, since we're dealing in parametric equations. So what does this mean? This means that I do the derivative with respect to t of y prime, so I'm doing the second derivative, so that makes sense. Second derivative, I'm doing the derivative again. So I've got the first derivative, now I'm going to do the derivative again. However, this part is where the trickiness comes in, because this says I also then need to divide that by, again, the derivative of x with respect to t. So to get the second derivative, I do the derivative with respect to t again of my y prime. But then I also have to divide it by the derivative of x with respect to t again. Okay? So this is the derivative of y prime with respect to t again. But this is the derivative of x with respect to t. And that's where the little hard to remember or hard to do part comes in. I mean, it's not hard to do, it's just hard to remember to do it maybe, but that's how you do it. All right, so let's just try one and see how it goes. Find d squared y over dx squared looks like. Just the second derivative, how we denoted here, for x equals t minus t squared, y equals t minus t cubed. Okay. The second derivative, so obviously start with the first derivative. Now remember, to get our first derivative, our dy over dx, however we write it, remember how we did it for parametric? Well, you just do the derivative of the y with respect to t over the derivative of the x with respect to t. I mean, we don't have to change it back to Cartesian equation. We can just do, this is how you can do this with parametric. You just do the derivative of that, which is 1 minus 3t squared, divided by the derivative of the x with respect to t, so it'll be 1 minus 2t. All right, we talked about that last time. Now, to find the second derivative, y double prime, but they have chosen here to denote it this way. How do we do it? Well, it's this. You got to do the derivative of the y prime with respect to t. But then you got to divide that by the derivative of x with respect to t. Now, to get the derivative of y prime, which is this, how are we going to do that? Well, now it's now it's a quotient, so we are going to have to use a quotient rule. We haven't had to pull that out just yet because of the original functions, but now the y prime is a quotient, and so yeah, quotient rule is what we're gonna do here. All right, so low, which is the way I remember it, times the derivative of the high, which is minus 16, minus high times the derivative of low, which is negative 2, and that's over low squared. Okay, but that's not the only thing we've got here, because the way this is constructed, the way it works, is now we also have to divide that again by dx over dt. So going back to the original x, what is dx dt? Well, it's just the derivative of that, which is 1 minus 2t. So this is dy prime dt, and then the bottom is dx over dt. Okay? Is that okay? All right, so let's simplify. That would be negative 6t minus 12t squared minus, if I distribute that, so it'll be plus 2, and then minus, that'll be minus 6t squared. Is that right?
Plus 12.
Oh, plus 12.
Yeah.
I thought you were talking about the other. All right.
But yeah.
Just checking, all right. Yeah, so minus, then a minus times minus plus. All right, then here, you see I got the plus 2 because you got a minus times 1 times negative 2, so that's positive 2. Now, this is divided by 1 minus 2t squared. And then this is 1 minus 2t. Fix that here in a second. All right. So combining what we can combine there, you got 12t squared minus 6t squared, so that's a 6t squared. And you got a minus 6t plus 2 over 1 minus 2t squared. And then, all right, so this means divide by 1 minus 2t. But what does divide by 1 minus 2t mean? Times the reciprocal, right? Yeah. So divide by 1 minus 2t means times 1 over 1 minus 2t. So what happens here? You got a 1 minus 2t cubed. And so I believe that, factor off of 2, but I don't think that'll help us much of anything. So is that okay? Yeah, so that's, usually because of the way this is constructed, you are going to wind up with a quotient rule here. And so it's easy to forget to leave off this dx over dt stuff, but you've got to divide, because of the parametric stuff, you got to divide by that dx over dt once again. Okay. So we'll do another one, but all three wound up over here. Usually don't have any over here. All right. So kind of an application. Remember one thing. All right, here. Find the values of t for which the curve is concave up. It's x minus t cubed minus x equals t cubed minus 3t. Y equals t squared. Okay, so we mention here this now because how do we know where a curve is concave up? Second derivative, isn't it? Second derivative is positive. Concave down, the second derivative negative. So this is an application of the second derivative here. So I need to find the second derivative, and then we'll talk about how we'll find it concave up. All right, so to get the second derivative, of course, we start with first derivative. And again, since it's parametric, the best way to go is just dy dt over dx dt. So it'd be 2t over 3t squared minus 3. With me on that? Nothing simplifies, we factor off of 3, but that wouldn't help us. This good? All right, so now the second derivative, which we have written, don't have to write it here, but then we'll throw it at, we'll just say find that, so you need to know that's the second derivative. Well, the second derivative with parametric is, yeah, you do dy prime dt over dx dt, dx over dt. Yeah, so you take, just like before, you do the derivative of that, but there's this extra little piece you got to throw in as well. So the derivative of that is our quotient rule, low, d high minus high, d low, over low squared. But for parametric, second derivative. There's also that you got to divide again by dx over dt. So it's just the derivative of the x again equation, which is 3t squared minus 3. And like happens a lot of times, yeah, those two are going to become a cube. Happens a lot for these second derivatives. All right, so what do we got? 6t squared minus 6 minus 12t squared. And yeah, because of you're dividing by that and reciprocal thing and all that, it's going to be, bottom is going to be 3t squared minus 3. Negative 6t squared minus 6 over 3t squared minus 3 cubed. Second derivative. All right. But the question was, where is this concave up? And so I want to know where that turns out to be greater than 0. But first, we also remember here, not only, okay, so the way we did these back in the day, in our Calculus 1 days, was we thought about the critical values, I think we call them. Critical numbers, critical values, but where this concavity breaks up, we're talking about second derivative, so we're talking about concavity. Where the concavity breaks up are at those critical numbers, which, remember, the critical numbers are where it equals 0 or does not exist, okay? So remember that the critical values here, where things change, you change from concave up to concave down, or something happens there. I mean, it may not change concavity, but the critical values tell you that. So it's where the second derivative equals 0 or second derivative does not exist. And actually, usually it wound up being, well, where it was equal to 0, it does not exist, didn't come into play, but here it does. All right, so if I set the second derivative equal to 0, well, multiply both sides by 3t squared minus 3 cubed. To clear that out, and it's just minus 6t squared minus 6 equals, and 0 times that is still 0. You got this, which, if we solve for t squared here, I think you see a bit of a problem. T squared equal -1. Can t squared equal -1 for real values? Yeah, there's no real solution here. So that's what I was saying. This one's kind of, I don't know if they all work this way, but this one, you don't get any value if you just do equals 0. So look at where the second derivative does not exist, which that usually, if you've got a fraction, what does that mean? Denominator equals 0. So that's 3t squared minus 3 cubed equals 0. So that's going to be 3t squared minus 3 equals 0. And so that's actually going to have solutions. Just cube rooted both sides. It gets down to that. Yeah, that's actually got some solutions. Add 3, divide by 3. You got t squared is 1. So t is plus or minus square root of 1, and plus or minus 1. And so you kind of think, it's not really, the xy number line, but you're kind of looking here at on the t values, t number line. Remember that that sets up 3 different places, and check your second derivative values, whether they're positive or negative. Because again, we're looking for concave up, which means the second derivative is positive. So just pick a number out of each one of these and see what happens to the second derivative. So in this one, in this part, if we do y prime, say of -2, So if I plug in t is -2, what do I get? Well, that's better be a positive 4, so it'd be -24 minus 6 over 12 minus 3. Is that right? It's cubed. Well, figure all that out, but it's going to be a negative value, isn't it? Because you got a negative divided by a positive. 9 cubed, is that 729? -30 over 9 cubed. It's a negative value. So the second derivative is negative there, so that's concave down. In between here, 0 would be a good one, so that would be -6 over -3 cubed. Now that's going to be a positive, because you got a negative divided by a negative. That's positive. So that's concave up there, and then out here, I think we're going to run into the same, plug in 2. Yeah, I think you get the same value as you do with -2. It's negative. So that's concave down. So it's in between there. So the question was, find the values of t for which the curve is concave up. So the values of t, so it'd be in here, wouldn't it? From -1 to +1, t is between those two. Is that okay, everybody? That's really recalling stuff from our past, searching the depths of your mind there, as they say. Is that okay, though?